The second derivative with the power rule. So in this video, we're going to be looking at higher order derivatives. So what are higher order derivatives? Well, we've already talked about the derivative, which is denoted with f prime of x, and we know that this represents the slope. And let's remember, another word for slope is rate of change, or how fast or slow our function is changing the height. Well, then another question comes into our mind. What if we want to know the slope of the derivative? Or what if we want to know the slope of the slope? What if we want to know how fast the slope is changing with a function? Well, that's pretty simple. We would just go ahead and take the derivative of the derivative, because the process of taking the derivative allows us to find the slope or the rate of change of whatever function we're taking the derivative of. So we would just take the derivative of the derivative. So we would have f double prime of x, and this is also referred to as the second derivative. And again, it's denoted by having those little 2 prime marks instead of just 1. Well, can we take the derivative of the derivative of the derivative? And the answer is yes. We can continue to take the derivative of derivatives and keep finding the rates of changes of the derivatives, or of those slopes. So we could take the third derivative, the fourth derivative, the 100th derivative, forever and ever and ever. Now, if we notice, when we take derivatives, the first derivative is 1 prime mark, the second derivative is 2, the third derivative is 3. Now, we could technically continue putting those prime marks, but it just gets a little bit ridiculous. So, the standard notation is that after we get through the third tick mark, we just put the number of the derivative in parentheses above the f. So we have the fourth derivative, or we have the 100th derivative, because no one really wants to put 4 or 100 tick marks. So we use this notation to just make it simpler. All right, so does this really define higher order derivatives? No, it gives us an idea what they are, so let's define them. So the second, the third, the fourth, the 100, these are known as higher order derivatives. Any derivative above the first derivative is a higher order derivative. And we can denote this by using a kind of weird formula. I don't want to say formula because we're really never going to use the formula, but we can denote that using this notation by saying the nth derivative of x is equal to the derivative of the n minus first derivative of x. And the only condition here for n is that n has to be greater than or equal to 2. And that's because we said that any derivative above the first derivative is a higher order derivative. So 2 or above represents a higher order derivative. Now, this notation is a little bit odd, and it's really not used very often except to define higher order derivatives, but let's just quick look at an example to kind of see how it works. So for example, we already talked about that the second derivative, f double prime of x, is equal to the derivative of the first derivative. So in this particular case, if we want to see what our n value is, we can say that our n value here is 2. And then if we compare it to what we're taking the derivative of, n minus 1, well, that'd be 2 minus 1, which equals the first derivative, which is what we have. So again, that's just kind of how the notation, or excuse me, that's how the definition works. So let's talk about other notations. So we've already talked about the double prime mark, f double prime of x. That holds true if we just want to take the derivative of y. That could become y double prime of x. But now if you're going to use our other notation, dy over dx, that would be d squared y over dx squared. And now let's just talk about why the squares are in a certain spot and why they aren't in certain spots. Because some folks like to think the second derivative is, oh, it's dy squared over dx squared. Well, if that was the case, notice how we're squaring the function y. And that's not what the derivative does. The derivative does not square the function y. So that's why the y is not squared. But if we think about it, the derivative, or the second derivative, is just the derivative of the derivative of y. And then if we multiply the derivative and the derivative, d times d is going to be d squared, and then dx times dx will be dx squared, giving us that notation. Well, then if we wanted to change notations and not use y and would rather use f, we could do that too. So then it would just be d squared f over dx squared to represent the second derivative. Now, fortunately for us, this notation is the most challenging part, and let me demonstrate that the actual taking of the high-order derivatives is much simpler. So here we go. Find the second derivative of the following function, and the function we have is f of x is equal to 5x to the fourth plus 10x cubed plus 3x plus 6. So, we're being asked to find the second derivative. Well, in order to find the second derivative, we need to first find the first derivative. So, f prime of x will come in, and we have a polynomial, which means it's just going to be all power rules here. So 5x to the fourth will be 20x cubed plus 10x cubed is going to be 30x squared, and then plus 3, because the derivative of 3x is 3, and the derivative of 6 is 0. All right, so now that we have the first derivative, we can now take the derivative of that function to get the second derivative. All right, so then the derivative of 20x cubed is going to be 60x squared, plus the derivative of 30x squared is going to be 60x. And then the derivative of 3 is just going to be 0, so that means we are finished. So therefore, the second derivative is 60x squared plus 60. Not too shabby. All right, in our next example, we're being asked to find the third derivative of the following function. Uh-oh, third derivative. Sounds a lot scarier than it is, because all that means is we're just going to take the derivative 3 times. So let's hit it. So first derivative, boom, 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 boom. Let's see, the derivative of 3x cubed is going to be 9x squared. The derivative of negative 5x is going to be, negative 5. And then the derivative of 12 is going to become 0, so we don't need to write that. I'm erasing too much. All right, there we go. First derivative, 9x squared. And let's take the second derivative, work our way up to the third. And let's see, the derivative of 9x squared is going to be 18x. And then the derivative of negative 5 is just going to be 0. And since we're looking for the derivative, we need to do this, since we're looking for the third derivative, we need to do this one more time. So f triple prime of x is going to be, well, the derivative of 18x is just going to be 18. And there we have it. The third derivative of the function is 18. All right, our next example is asking us to find the second derivative of the function negative 4x to the fifth, but this time it wants us to find the second derivative at the x value, negative 3. So, as always, or not always, but as of today, in order to find the second derivative, we need to find the first derivative first. So, f prime of x is going to be, let's see, negative 20 x to the fourth. And then we need to take the derivative again to find the second derivative, which will give us negative 80 x cubed. But again, we're not trying to find the general second derivative. We want the second derivative at x equals negative 3. So we'll take our second derivative, we will substitute in negative 3, which will give us negative 80 times negative 3 cubed. Well, negative 3 cubed is going to give us negative 27, and then negative 80 times negative 27 ends up being 2,160. And there we go, the second derivative of f of x at x equals negative 3. And our last derivative. So here, we're trying to find the fourth derivative when x equals 2. And we're given the function f of x is equal to 10x to the fourth minus 32x squared. So, in order to find the fourth derivative, we got to take the derivative 4 times. So we're going to have f prime, which let's see is going to be 40x cubed minus 64x. Then the second derivative is going to be 120x squared minus 64. The third derivative is going to be 240x. And then finally the fourth derivative, so f4 of x is just going to be 240. All right, but again, we don't want the general derivative. We want the derivative at x equals 2. So we're going to take the fourth derivative of 2, and, how do we plug 2 into 240? Well, we don't. So what is this, like, how do we answer the question? What does this 240 mean? Well, great question. Let's just quick sketch a graph of what we have here. So we can see that the fourth derivative is 240. And 240 is a constant function, which means it doesn't matter what our input is, the output is always going to be 240. So the fourth derivative of 2 is going to be 240. The fourth derivative of 17 would also be 240, and the fourth derivative of negative 4,762 would also be 240, but that's not what the question asks. All right, folks, and that is finding the second derivative with the power rule.